In this video, we are going to be looking at the halogens, which are our group 7 non-metals. So at the top, we have fluorine, and you need to know that when these halogens are by themselves, they are always going to be diatomic. So we have F2 here, and then Cl2, Br2, I2, and then At2. Okay. So as we the first thing we're going to do is look at the boiling point trend as we go down the group. Okay, so we need to know what state these are all found in. Fluorine at room temperature is found as a pale yellow gas. Chlorine is a pale green gas at room temperature. Bromine is orange, brown, or red. You can use any of these colours to describe bromine, but it's a liquid. Iodine is found as a grey, black solid. Now, acetine has never been observed because it's very radioactive, but we can assume that it's a solid based on the trend as we go down the group. Okay, so we now need to explain why is it gas at the top, liquid, and then solid. So clearly you can see that the boiling points increase as you go down the group, so do the melting points as well. We need to explain why. So first things first, we need to know what structure they adopt. Because these are covalent molecules, so within the molecule, they have strong covalent bonds. The structure that they adopt is simple covalent molecules. Okay, so these are simple covalent molecules. Within molecules, there are strong covalent bonds, but between molecules, there are weak intermolecular forces. So for this one, we're going to have London forces, and all of these have London forces between the molecules. So at the top, remember, London forces depend on the number of electrons. Fluorine at the top doesn't have that many electrons, but as you go down the group, the number of electrons increase. Okay, so as you're going down the group, the number of electrons increase. And what that does is that the dipoles that are induced are going to be stronger, and therefore the London forces are going to be stronger. So as we go down the group, we have stronger London forces. And because we have stronger London forces, they require more energy to break. And because they require more energy to break, that means the boiling point has increased as we go down the group. Okay, so you need to be able to explain why the boiling point increases as we go down the group. And the reason being is because the London forces increase as we go down as the number of electrons increase. Okay, before we move on, we're just quickly going to discuss the reactivity as we go down. I will explain the reactivity later, but you should already know that as we go down the group, as we go down group 7, the reactivity decreases. So fluorine is the most reactive, and as we go down, the reactivity decreases. So acetine, we can assume, is going to be the least reactive halogen. In terms of their electron configuration, so each halogen is going to end in, because they're group 7, they've got 7 outer electrons. So the electron configuration is always going to end in S2p5. The outer electron is an a p subshell, and therefore they are classed as p block elements. And as we can see, in order to become a full shell, its outer shell to become full, we need to gain 1 electron. So if we have a molecule of F2, each fluorine atom must gain an electron. So therefore it's going to gain 2 electrons because there's 2 here. And then they become halide ions. So this over here is a fluoride ion. Okay, so this is an example of a halide ion. If we have, for example, Br minus, it's still a halide ion, but this is now called a bromide ion. For chlorine, it's going to be chloride. Iodine, it's going to be iodide. Okay, so in terms of what's happening here, so all our halogens want to gain an electron, and therefore we can class them as being reduced. And if they're being reduced, something else must be oxidized, and therefore halogens can be classed as oxidizing agents. Okay, because they themselves are being reduced, but they are oxidizing another species. Okay, let's have a look now at a reaction that halogens can undergo. And these are displacement reactions, which you should have done at GCSE. Okay, so in terms of displacement reactions, we can have a halogen that's part of a compound. So for example, we can have bromine that's part of the compound. So we've got sodium bromide here, and we can have a solution of this. And what we can do is react it with a solution of chlorine. So imagine we've dissolved some chlorine gas in water, and we can then have a solution of chlorine. Okay, the thing to know here is that, so this is the halogen, this is the halide, so this is Br minus here. If the halogen is more reactive than the halide, it will displace it in the compound. Okay, so over here we've got chlorine, which is above bromine in the periodic table, and therefore it's more reactive. So here chlorine will displace bromine, or bromide, sorry. So we'll then end up with NaCl. And because it's kicked it out, bromine is then going to be by itself. And as we know, when it's by itself, it's going to be diatomic. And that will also be aqueous because everything is dissolved in solution here. Okay, and then just to balance it, we've got that. So this displacement reaction does occur because chlorine is more reactive than this halide ion here. So it will essentially kick it out. And the same thing happens with a few other reactions. So for example, let's say we've got sodium iodide, solution of that. And let's say that we have some bromine solution that we mix with that. Now over here, bromine is above iodine in the periodic table, so it's more reactive. So bromine here is going to kick out the iodide ion and take its place. And then iodine is going to be kicked out, so it's got to be diatomic when it's by itself. And again, just to balance that, we've got this. Okay, and we can show that these are redox reactions by putting in oxidation numbers. So for example, let's do it for this one here. Sodium here is +1, iodine is -1, uncombined element 0, +1 here, -1 there, and 0 here. Okay, and we can see that sodium hasn't changed, so it's not taking part in the reduction or the oxidation. If we look at iodine, iodine goes from -1 to 0. Okay, so over here it's lost an electron and therefore it's been oxidized. And if we go for bromine here, bromine goes from 0 to -1, it's gained an electron and therefore it's been reduced. Okay, so clearly we can see that these are all going to be redox reactions. Right, the next thing we need to do is what we'd observe in this reaction. Okay, so in both of these reactions, so these solutions here, so whenever you have these salt solutions here, they should normally be colourless. And what you should observe in this first one here, so chlorine is going to be a pale green gas, but when it's in solution, it's pretty much colourless. But bromine, as we know, is going to be a red, brown, or orange colour. I tend to just go for orange. So what we do observe in this, so if we're mixing together two colourless things, we've got a colourless thing here, but we've got an orange solution here. So for this one, we should observe an orange solution. So it should be a colour change from colourless to orange. Now over here, again, we've got a colourless solution. Bromine, as we know, is an orange solution, so it is going to start off kind of an orange colour. We've got colourless here. Iodine, I know I said it was a grey-black solid, but when this is dissolved in solution, this also gives an orange-brown colour. And as you can see, that's very similar to the colour that our bromine has over here. So we are going to hit a bit of a dilemma here, where when we do this reaction here, we don't see much of a colour change because it will still start off as an orange colour and end up as an orange-brown colour. And because those two colours are difficult to distinguish, we do use something else to distinguish iodine solution from bromine solution. So in terms of colours, when we have them in solution, okay, when we have chlorine by itself in a solution, it tends to be a very pale green solution, pretty much colourless, okay. Bromine in solution is going to be an orange solution, and iodine is also going to be an orange-brown solution. Okay, in terms of distinguishing chlorine, it's pretty straightforward, but bromine and iodine are difficult to distinguish. Okay, so what we do is we dissolve that in some cyclohexane, and cyclohexane is a non-polar solvent, and what happens is that these dissolve better in non-polar solvents. So if we put chlorine into cyclohexane, again we're going to see a pale green colour. Bromine, we see orange, but iodine now in cyclohexane is going to be a very strong violet colour. Okay, so when we add cyclohexane, we can now clearly distinguish between these three, because iodine's violet, bromine's orange, and chlorine is pale green. Okay, so in terms of the reactions that do occur between these halogens and halides, if we now just, I'm going to sketch a quick table. So I'm going to have the halogens at the top and the halides along the sides. Like this. We don't really react together the same halogens because there's no point of doing that. So I'm going to cross those out. Right, if I add bromine solution to something chloride, so for example sodium chloride, bromine is not more reactive than chlorine, so it won't kick chloride out of the compound. So this reaction here, you won't see any observation because there'll be no reaction. And the same thing happens between iodine and chlorine. So iodine is not reactive enough to kick out the chloride ion. So again, no reaction here. And iodine is not reactive enough to kick out the bromide ion. So again, no reaction here. Okay. Over here, as we know, chlorine is reactive enough to kick out bromide. And therefore you will have a reaction here. And we should observe an orange solution here. Okay, it's going to be orange in a solution, and also when we add cyclohexane to it, it will still be an orange-brown colour. Okay, right, when we add chlorine to something iodide, chlorine is more reactive, so it will kick out iodine, and therefore you should see a reaction. It is going to form an orange solution first, but when we add it to cyclohexane, we should then observe a violet colour change. And the same thing for this one as well, because bromine can displace iodine like that. Okay. Right, let's now discuss these in terms of reactivity. So why is it that the halogens, as you go down the group, become more reactive? So I'm just going to list the halogens again. Okay, so remember the aim for the halogens is that they want to gain an electron. Okay, as we go down the group, in terms of gaining an electron, the size of the atom is going to affect it. Okay, so as we go down the group, because we've got more electron shells, the radius increases. Okay, and as I said, because we're getting more shells, the shielding will also increase. And because of this, the nuclear attraction to the outer electron decreases. And because there's less nuclear attraction, it's very difficult for the species to get an electron from elsewhere. Okay, so it's difficult to gain an electron. And that's why as we get down here, it's very difficult to gain an electron, and therefore we say the reactivity has decreased.